Hello, everyone. Today we will talk about economies of scale as an interdisciplinary topic. And so we will introduce this very important economic law, but then we will see the implications, not in real life, but especially in computer science, that is, some computing devices that use the same principle. Let's see if we can get the screen sharing to work. And so let's begin our discussion by looking at the fundamental law of profit. In the business world, companies are constantly striving to maximize their overall profit, and we can very well simplify this entire concept by observing that at its core, profit is simply formed by taking the total revenue and subtracting the total cost. Revenue represents the total amount of money that a firm manages to collect from the sale of its products and services. On the other hand, the cost is defined by all the various expenses that the company incurs during the production of the goods that it then has to sell to its customers. Essentially, this distinction is fundamental to understanding the overall financial health of any business. We can replace revenue with this product, we can represent it better with this product, which already gets us into the discussion we need to have, because while this refers to the entire production, this whole formula, if we want to detail it, let's imagine for simplicity that the firm has only one product. Revenue can be represented by the product of the unit price and the sales volume, therefore the number of pieces sold times the price of each piece. Normally, when you are looking to increase your overall profit, you really have two main levers you can pull. You either need to obtain a much higher sales volume, or alternatively, you try to increase this sales volume significantly, or perhaps you focus on raising the unit price of your products. If you increase the price, we know that the law of supply and demand, however, gives us negative feedback on the sales volume, and therefore it is not the best idea. Increasing sales volume, on the other hand, is good, for example, with advertising, and it leads to an improvement in profits. We also have this term, however, the cost term. It's a negative term, so we need to try to decrease it. Economies of scale, let's say, act on this term. Let's look a little more in detail at the topic of costs. We can divide costs into fixed costs and variable costs. This, however, does not concern time, at least in our discussion. We must each consider fixed and variable with respect to another parameter, which is the production volume. So, what is a fixed cost with respect to production volume? It could be, for example, the cost of infrastructure, more specifically the rent of the warehouse, if we are talking about a manufacturing type of production. The warehouse rent does not vary within certain limits, whether production is very low or whether production reaches very high levels. For example, we can say whether production is done 1 day a week or whether this production is done for 6 or 7 days a week. Obviously, the production volume will vary, but the rent cost remains fixed within these limits. An example of a variable cost in the same situation could instead be the cost of raw materials. The cost of raw materials follows the production trend more closely, and therefore the production volume. If I need to increase the production volume, I must also increase the cost of raw materials. Regarding this breakdown, therefore, we can normally further simplify variable costs by considering the production volume itself. Every product we have has its own fixed cost, which in this case we will call unit cost. By multiplying this cost by the production volume, we get an idea, an estimate of what these variable costs are. At this specific point in our analysis, however, we really must shift our focus away from reasoning about the entire production process as a whole and instead move toward reasoning about each single piece individually. By doing so, we are finally able to accurately calculate the specific cost associated with every single unit produced. And if we have the total production cost, we divide it by the production volume, that is by the number of pieces produced, and we obtain this specific cost. But since we have established the production volume, let's say, in this way, fixed costs plus variable costs, well, we have fixed cost divided by production volume and variable cost divided by production volume. We have expressed the variable costs based on this product, and therefore we find the production volume in the numerator and the production volume in the denominator. So we can simplify By following this calculation, we obtain this little formula for the specific cost of the product. Essentially, we have the total fixed cost divided by the overall production volume, and to that figure, we simply add the variable unit cost to reach our final result. We see that the effect of the variation in production volume on the specific cost of the product is an effect that perhaps doesn't come to mind immediately. It is a contrary effect, let's say, in the sense that by increasing the production volume, the cost of the specific product decrease. This tells us this is the principle of economies of scale. If we increase the production volume, our product will cost us less. This is a great advantage because it will then also allow us to lower prices, to be more competitive, and therefore to sell more products. It is in principle one of the, let's say, fundamental economic laws that regulate the economy today, let's say, and over the last, as I told you, 30, 40 years, this term is called the amortization term, where the fixed cost is a quantity that does not change. The more products I manage to make, the more I amortize it, meaning this fixed cost has less impact on the specific cost and therefore on the final price. This, in fact, is the economy of scale. This economic principle in itself is already quite important regarding the economy, but it interests us because we find it in everyday life, and now I will give you an example. We also find it very often in computer science. So in everyday life, I remember that when I was a child, we would go grocery shopping almost every day, going to the shop down the street to buy what was needed day by day. Today, however, there is a tendency, a trend, if you will, to go grocery shopping once a week, doing a larger shop, and therefore concentrating the shopping into a single day. What is special about this? The principle is always the same. That is, what is being amortized, in this case, the term I have marked here for you in the case of grocery shopping, is time. Time. Dead time of this process, let's say, is amortized by concentrating the production, so to speak, that is our grocery shopping, into a single day of the week, obviously while increasing the volume of production, which in this case is the volume of our shopping. That's one example. You can find others in real life, let's say, in everyday life. But what interests us most is seeing what computer science has to do with it. Well, in computer science, in IT, there are various examples of the application of this same process, and we can reason about it. For example, cache memory. What is cache memory? Cache memory is a very fast intermediate memory that sits between the microprocessor and the main memory, and it is used precisely to amortize a fixed cost. We will see better what this is about later in a subsequent video. The speed of file transfer over the network is another aspect, different, let's say, from the previous one, but it still concerns computer science. And in this case, what are we amortizing? The transaction time. The transaction is a period in which there is no actual exchange of information, at least not the content, the object of the file that is, needs to be transferred, but in reality, information is exchanged to agree between the sender and the receiver on the type of transmission. There you go. This transaction is dead time. We will see that this dead time influences the transmission speed. Since this will be very similar to cache memory, I won't give you a specific lecture on it, but I will associate it with that of cache memory. We will therefore see that perhaps we will obtain results that at first glance will seem a bit strange. However, once we have clearly clarified the terms of what we are saying, I think we will be convinced of these results. Amdahl's law, lastly, is a law that concerns the multiprocessor systems. Well, contrary to what one might think, adding more processors doesn't always make things go faster. In fact, we even see a non-linear trend that reaches a maximum and then actually starts to lose speed as you add more processors. So it has a somewhat strange non-linear behavior. This behavior involves the amortization of a fixed cost, which in this case is the initial time required to start up each processor. All right? So 3 examples from computer science that relate to the law of economies of scale. I had included a graph here, which I forgot to mention earlier, regarding economies of scale in, let's say, its extension. We can see that the trend of this mathematical law of this mathematical function is also a non-linear trend that leads us to a general reduction. In this case, the x variable is this production volume and the y variable is the specific cost. We can see that we have a trend of this kind, that is, as the production volume increases, we have this decrease in cost. I should have written specific cost. Is that okay? Okay, so this is fine for the first video. Then we will see the other things in more detail in the following videos. See you next time.